welcome to the seminar. We're going to get started. Today we have Jonathan Colby speaking to us in person for once. And Jonathan is the president and founder of Streamwise Development, a client-driven consultancy focused on enabling innovation and commercialization in the renewable energy and aerospace industries. So whenever you're ready, go ahead.
Totally. Well, good afternoon, everyone. It's a pleasure to be here, the in-person part especially. Thank you, Martin, for the invitation. And thanks to y'all for organizing everything. Again, I'm Jonathan Colby. I'm going to talk today about the path to commercialization for the marine energy sector. Commercialization as a term really means to adopt in the mass market. And so what we're really talking about is how to take these technologies out of the lab, out of R&D, and into broad adoption as a piece of the renewable energy portfolio. And when I think about path, it implies a point A and a point B, and then some method of getting from point A to point B. So for today, I'm going to take that kind of approach as we talk about this path to commercialization. So we'll start with where are we now? What is the state of the industry as we sit here today? Then we'll look a little bit at where we're going. So what is the vision for the industry in 5, 10, 25 years from now? And then how are we going to get there? Like, what is that roadmap? What are the steps that we need to take to achieve that vision? And a Q&A, I love a dialogue. So if folks have questions, they want to stop me, raise a hand, shout it out. Super open to that. So, just let's make it interactive if that's what you guys feel. So we'll get started, right? So where are we now? So what I want to do is share a little bit about the US specific industry for marine energy. I'll step out a little bit and talk about the global industry and what's going on kind of around the world in marine energy. And within that context, we'll talk about some of the challenges that the industry is facing. And for every challenge, as an engineer, you can also see an opportunity. So we'll sort of frame where we are now in terms of both the challenges and the opportunities that presents. So to start with marine energy in the US, a big piece of it is what is the resource? So what do we have to convert from the oceans and rivers into electricity for use? So this is a map that was developed by NREL and the United States Department of Energy. You can see a number of different colors that are mapped to the continental United States, Alaska, Hawaii, and a number of the island territories. The light blue is what we have for an ocean current resource. The kind of medium blue is our wave resource. The orange is a tidal resource. The hashed gray is called ocean thermal energy conversion. And we'll talk a little bit more about that throughout the talk today. And then the dark blue is our riverine resources here in the United States. And so kind of one of the key pieces to focus on is right in the center, which is the total technical power potential for the United States is on the order of 2,000 terawatt hours per year. Not necessarily a meaningful number. What is meaningful is that the entire consumption in the United States is around 4,000 terawatt hours. So something like half of all of the United States energy consumption could be met by the technical power potential of the marine energy resource. Now, you can't capture all of the technical resource, but even capturing a meaningful percentage of that resource directly leads to a meaningful percentage of the United States energy demand being met by resources from our marine environment. And so it is a substantial resource. And so where we are now is really understanding that there's a huge resource available. And for the most part in the United States, it is untapped. Then we look in the US on the technology side. I'm not going to show an example of every one of these technologies, but I just wanted to show you some of the companies that are here in the United States doing it. And so these are some of the leading companies. On the left, you have all of the tidal and current energy converters. So the Qantas, Emergy, Literal Power, Ocean Renewable Power, which is ORPC, and then Verdant Power. And I know that you had someone from Verdant here a couple weeks ago, maybe a month ago. I'm not exactly sure when they were here. So formerly, I spent 15 years at Verdant Power. I was previously the director of technology performance at Verdant, and I led their Roosevelt Island tidal energy project. And you'll see 1 or 2 photos of that project. I know those guys, Irwin and Leighton, talked about the tri-frame and about the Verdant Power Gen 5 turbine. So that's some context of what a tidal energy converter looks like. On the right are some of the leading wave energy developers in the United States. So Sea Power is Columbia Power, CalWave, Ocean Power Technologies is OPT, Acilla Power, and then Resolute Marine. We'll talk a little bit later. There are a lot of job opportunities right now in the marine energy space. And so this is really an area where if you're interested in marine energy, interested in ocean engineering, this is a place where there are jobs, and especially for folks coming out with masters or PhDs, there are a lot of opportunities in this industry if you're interested in working in this space. My email's at the end, and we can talk, afterwards and offline. I'm happy to connect you to some of these companies if you're interested in any of these specific technologies. So as we step out, the US has a pretty thriving market, and we'll talk about the funding mechanisms and a lot of that in a few slides. But at the global level, there's a lot of stuff I also want to share with y'all. And one of the key places and repositories of this information is the International Energy Agency, or IEA, and their ocean energy system. And this is a partnership of about 20 countries around the globe, bringing together expertise and thought leaders in the industry at a sort of international level. They have a number of publications that sort of summarize the activities globally of the industry. So if you're interested, I would certainly encourage you to kind of research more about the OES. Two of the reports that I highlight here, I think are really relevant. On the left is the State of the Science report, which summarizes the environmental effects, the science behind it, the unknowns, some of the risks that have been retired. And I'm sure you've heard in a lot of these marine talks, protecting the environment and ensuring the compatibility with the environment is a huge challenge. And one of the major hurdles that a lot of these developers have to overcome is proving these devices are compatible with the environment. When we first started, I know when I first started, killing fish was the biggest concern. And there would be lots of jokes about like sushi downstream of these rotating blades. And, you can imagine that whole suite of jokes that come. So proving that these devices are safe and are compatible with the environment is a huge part of what we do as an industry. And so if you're interested in the detailed sort of science of proving the environmental capability or compatibility, this IEA-OES report is a really good place to look. On the right, they do an annual report that summarizes the global activities in marine energy, and they do one of these each and every year. So it's really a great place to track and follow the progress globally. And so I'm going to now sample some of this report to show you the sort of spectrum of both geographic, occurrences, but also the different technologies that are being used for this conversion of the marine resource into electricity. So here we see the wave side of the world. And so you can see a suite of wave energy converters that have been deployed globally. In the upper left is the Sharp Eagle in China. And the reason I highlight that one is if you saw the brochure, there's a picture of me standing in a blue life vest with a hard hat. I'm actually standing on that wave energy converter in the upper left corner out in the South China Sea. And so one of the cool things about being in marine energy, and you guys know doing ocean engineering, is you get to be on the water and you get to be near the water. And that's certainly one of my favorite parts of like working in this space is the amount of time I get to spend on and around the water. In the mid rows and kind of top and bottom is all the stuff going on in Europe. Europe is really the leader in the marine energy space. So you see projects in Spain, Sweden, France, Denmark, etc. Lower left is a really interesting one. That's an Irish company that designed a 500 kilowatt wave energy converter. They had it built in Oregon, and it was towed across the Pacific Ocean out to Hawaii for testing at the Wave Energy Test Site in Hawaii. So it truly is a global industry. And you see lots of these global partnerships where a developer in one country is leveraging testing capabilities in another country, for example. So hopefully that gives a sense of just the broad geographic, but also visual differences in these wave energy converters. On the left, you can see some of the challenges and opportunities. One of the big ones for wave is that there has been a real lack of technology convergence. And so you see this huge spectrum of wave energy converters. Some of them bob up and down as a point absorber. Some of them flap as each wave goes by. Some of them articulate. Some of them actually use the air above the waves in an oscillating air column to drive air turbines. So there's this huge suite of technology in the wave space. That lack of convergence is a significant challenge, actually, because each one of these new technologies is innovative and new in and of itself. And so you have to de-risk that system, you have to qualify the technology, and it's perceived as a relatively high-risk industry. And so one of the things we'll talk about as we go on in this talk is how do you de-risk and how do you reduce the risk of this technology? And that's one of the key pathways and mechanisms to actually commercialize this industry is to reduce that risk so that insurers, investors, regulators all feel more comfortable investing, insuring, or allowing these to be deployed in your local environments. On the tidal side, it's actually quite different. In the tidal space, we've seen a pretty strong convergence of technology towards what basically looks like a wind turbine. And so what you see are these horizontal axis, 3-bladed, in some cases 2-bladed rotors that have basically the same physics of a wind turbine, except water as the working fluid instead of wind as the working fluid. So you change the turbulence, you change the density, the viscosity, but in general, the physics is pretty well understood. And so the perceived risk of these tidal and current converters is oftentimes lower than the perceived risk of the wave devices because there are models for wind turbines. You can take off-the-shelf load prediction tools, off-the-shelf grid integration tools, et cetera, which really helps people feel more comfortable with these technologies. Middle center is the Verdant Power tri-frame that you all saw in New York City. That's sort of the premier US platform for tidal energy. That project did over 300 megawatt hours of electricity to the New York City grid. And as I said, I know Erwin and Leighton were here and did a really great job of explaining that. The upper left is another one I want to highlight. That is the world's largest tidal energy project. Eventually, it will be up to 400 megawatts of tidal energy in the northern part of the United Kingdom. The company CMEC Atlantis has deployed 4 of these 1.5 megawatt devices. For scale, that Verdant device is only about 100 kilowatts. So that single turbine up above is about 10 times more powerful than the tri-frame of Verdant turbines. As we talk about commercialization, scale is another huge one. So the bigger you go, the more power you get, really helps to commercialize because it really helps to bring down that levelized cost of energy. If you remember from sort of basic physics, the power is proportional to the area, which is the diameter squared. And so if you double the diameter, you get 4 times the power. So by getting larger and larger turbines, you get much more energy. The other relationship is that power is proportional to the cube of the velocity. So if you double the velocity, you get 8 times the power. So on the tidal side, what you're looking at is people going to deeper water, which lets you have much bigger turbines, and faster water, which lets you get, in addition, even more power. So you'll see a lot of these are much larger. You have a megawatt for Nova Innovations, 1.5 megawatts for Magallanes in Spain. One other really interesting one is the Monesto kite, which is in the center right. It is a tethered kite system that uses a series of figure 8s that create an increased relative velocity at the rotor disc. So you can operate this in a very low speed environment or a very shallow environment. And by having this device move in these figure 8 patterns, the relative velocity at the rotor disc is increased. And so you get more power than you would for a stationary object. So really, I mean, if you look, with the exception of that Monesto and maybe that HydroQuest, pretty much all of these are 2 or 3 bladed horizontal axis turbines. So you have that technology convergence. A big challenge for tidal is that we have yet to see the long-term deployments. So we've seen deployments of 1 year, maybe 2 years. I know Martin's really proud that they've had a device out there for 3 years. 5 to 10 years is a minimum of what we need to start seeing. 20, 25 years is what we really need to start seeing, because that's where you validate your service interval estimates and your lifetime estimates. And that cost of that over the whole life, that cost is a really big driver from an insurance and investment perspective. So some of the activities globally in the tidal and current energy space. So I'll pause there for a second if anyone wants to talk about where we are. Yeah, please.
You mentioned risk a couple of slides back. What risk are you specifically talking about? Like risk to humans, financial risk, all of the above?
Yeah, that's a really good question. So the short answer is all of the above. I think the near-term risks, the first one was risk of environmental damage. So are you killing birds and fish? Are you adversely impacting the predator-prey dynamics in an area? Are you leaking chemicals? Do your power cables emit some kind of EMF that's messing with fish? Are you making noise acoustically from your turbine that could interrupt behavior in the water? So that environmental risk is a big one. Risk of machine failure is another big one, because if you put all this capital expenditure into a device, you go in with a 5-year plan and after a year it's failed, right? That's a huge risk that you're looking to avoid. Unlike oil and gas, these are almost always unmanned platforms, and there are generally very few people out there except for the boating community. So the risk to humans is not as great as it might be in a wind turbine where it could fall over into a place that's heavily populated, for example, or heaven forbid, a nuclear accident where you've got real risk of people around you. So yeah, I would think environmental risk, machine risk, and then financial risk are some of the 3 main risks that we're looking to mitigate as we bring this technology forward.
Thank you.
Yeah, of course.
I did have one more.
Go ahead.
So, Verdant Power, when they came, I had this question as well. I didn't actually ask it, but there was one of your first slides was the total energy resource that the U.S. has. But then you also mentioned that scaling up is really important to actually make it like profitable or work.
Commercialize it.
So to my knowledge, I think the biggest resources, you said that like we need deep water and we need fast current, right?
For tidal.
To me, that says Alaska.
Yep.
But there's no one in Alaska. So, and we don't have really great ways of transporting power. So there's not really much incentive to put it up there because it's not, the power won't be used unless we like have some place to store it. So is there anywhere else in the US that's like maybe California, but
So there's like multiple parts to this question. So the first of which is that there are lots of people in Alaska.
There are.
And we're going to talk about this later on. In those remote communities, the cost of electricity is incredibly high because they're being mailed in or boated in by plane. And so we're going to talk about this in the Powering the Blue Economy section of this, about how marine energy can satisfy specific niche or remote community markets and take people off of diesel gen sets and get them onto using resources locally. In that Alaska, in that southern part where you see the bright orange,
southeast.
that's southeast, that's where all the people are. And you have the higher grid transmission. So in that case, they are relatively well co-located. But another really fascinating part of this is this emergence of the green hydrogen economy. And hydrogen is actually a really viable storage vector. And they're looking at hydrogen-powered ships, hydrogen-powered fuel cells. And so producing hydrogen and then using that hydrogen for other industries is one way of taking that energy and making it more useful. So it's not only electricity, but there are these intermediate storage vectors. People mostly talk about battery storage, but there are actually a lot of other really interesting storage vectors that can be used to offset the maritime community in particular. So we'll talk about some of this in the next few slides, actually.
Sweet, thank
Yeah, in
you.
the back, please.
You mentioned that sort of deeper and faster is what's practical. If you were to relabel this slide and say practical power potential in milliwatt, whatever, terawatt hours per year, like, what do you think that number would be?
I think reasonable targets are to try to get 25% of this technical power in the near future. Would be reasonable. And then if you take 25% of a half of all the power, was another, it's like another 25%, right? That'd be like 25% of the whole US. Yeah, and 12, yeah, thank you, 12%. Exactly. So yeah, that would be a target. Is if we could get up to like 10% of the energy capacity from the marine environment in the US would be a reasonable target for us. And I have some slides on our capacity targets. And so we'll talk a little bit about what meaningful capacity targets we're actually trying to reach, both in the US and globally. Martin's back there snickering. What do you got?
I'm expecting you're going to have some slides on EMEC and their hydrogen experiments.
It's funny, not in this deck, but we can talk about it. We can. So I think I was here. So that's kind of where we are. And I love the question. So for sure, like keep this up. So where we're going, we want to be spoken of in the same sentence when people say the wind and the sun, we want them to say and the water. And so I think the relevant examples are the other renewables. And so I want to show you one example from the solar industry and one example from the wind industry, because those are industries we emulate. As I talked about on the tidal side, especially, we literally are emulating the wind industry. Like we are literally putting wind turbines underwater. But from just the renewables in general, we want to see the kind of growth that is shown here. And so this is installed capacity of US solar over the last, say, 15 years. And you can see until about 2010, 2011, the capacity installed in the US was relatively small. And in that last 10 years, we've basically seen a 10 to 20x increase in the installed capacity of solar in the United States. One piece I like to show, and we're going to talk about standards and the importance that standards and certification play in commercialization, is that the Technical Committee 82 develops international standards for solar photovoltaics. And in 2011, they developed this power quality assurance task force. And it's because they were seeing increased failure rates and poor performance in their solar panels. And the solar sector really prescribes a lot of importance on the improvements in quality of the individual panels, the inverters, et cetera, as leading to this dramatic rise in adoption of solar technology. Similarly, as you increase adoption, costs tend to come down. And so you get into this very positive spiral where more is installed, costs come down, so more is installed, and costs come even further down, and so more is installed. This is a model that we see is directly correlated to the marine energy sector. As you get more devices in, as quality is confirmed, reliability, performance, you get more of them in the water, price come down, you get even more in the water, et cetera. And so we aspire to a growth curve like this in the marine energy space. And this is from a colleague of mine, George Kelly, Tereska, always gives shout outs when somebody gives you an awesome figure. So on the wind side, which I think is even more relevant because of some of the physics that are so similar, this plot shows rotor diameter on the y-axis in meters over time on the x-axis, with the megawatt capacity superimposed at those key milestones of meters. And you can see that about 30 or 40 years ago, they were looking at about 100 kilowatt units with relatively small rotor diameters. That's Verdant Power. Verdant Power had a 5-meter diameter times 3, offering about 100 kilowatts. Wind, as you can see, dramatically increased their rotor diameter, and correspondingly, the power went up. What's not shown on here, which I love to talk about, is in 2020, if you put that out here, you could not fit where turbines are on this graph at all. At the moment, the world's largest offshore wind turbine has a diameter of 220 meters, and it is a 14 megawatt unit. This is the GE Halide X. It's literally as tall as the Empire State Building or like up in that area. I learned this crazy stat. One rotation of that turbine, so blade tip, top, all the way around and back, can power one house for 2 days. One rotation of this turbine produces so much electricity that it's a house for 2 full days. So just a sense of the scale that wind turbines have gotten to. So again, direct correlation and analogy here. As we get to larger diameters, as we get to better performance, improvements in the system, we expect to see these diameters grow and grow, the power grow, and eventually we get to this utility scale commercial adoption of marine energy technology. Similarly, standards played a huge role in the success of the wind energy sector. It wasn't until 1995 that global standards were even begun to be written for the wind energy sector. And it's no surprise that not long after that, the adoption of those standards, the codification of best practices led to this rapid growth in the size of turbines and the associated power that these turbines were producing. And then one other piece, which I'll talk about in the end of this, is what's called the IECRE, which is a global certification system for renewable energy equipment. And so this is where third parties verify the compliance to those standards. And we've seen that after this system was established, as I mentioned, this growth has even accelerated faster. And we're seeing these megalithic wind turbines being designed and deployed and operated globally. So, there is hope, I think, is really the takeaway of these 2 slides, is that we've seen these other renewables really take off. And we believe that following similar pathways and models can bring marine energy into these similar levels of meaningful penetration in the energy production in the United States. This is from my good friend Bob Thresher at NREL. Again, got to shout him. So capacity targets, and I think this gets to some of the questions in the back. The globe, different countries are putting out different capacity targets. You can see the US is slightly less aggressive than some of our colleagues in Europe. The US has roughly set a goal of 1 gigawatt of installed marine energy capacity by 2035. In the UK, they have a more aggressive target of 1 gigawatt by 2030. And post-Brexit, the UK is no longer in the European Union. So the European Union has their own targets. I will say the UK has a huge tidal energy resource, huge tidal energy resource. So it's not surprising they have such an aggressive target. But in Europe, they're already looking at 40 gigawatts of marine capacity by 2050. So 25 years out, they're already trying to plan the regulatory frameworks, the funding strategies, the technology incubators, et cetera, to try to meet this 50 gigawatt installed, or 40 gigawatts, I'm sorry. And I just wanted to juxtapose that against the potential resource for OTEC. And so OTEC, for those not familiar, is ocean thermal energy conversion. And it takes advantage of hot water at the surface of the ocean and cold water very deep in the ocean. And it creates a cycle where the hot and cold water are interchanged and you can produce electricity from that cycle. And so to get the maximum gradient, you need to be where the waters are the warmest, which is why you see most of the potential aligned with the equator, where you're going to have the hottest surface temperature and you're still going to have that cold, deep water. And if you look in the top, it's a little difficult to see maybe, but they estimate that there's 7 terawatts of potential in the OTEC space. And so 7,000 times the capacity targets just in this one resource alone. So again, this massively untapped resource globally. So now this gets into some of the other questions, and I'm going to touch literally on what was going on in Alaska. So another key piece of commercializing the sector is finding other niche markets where the current cost of energy is competitive. And I haven't yet touched on it, but one of the problems in marine energy is that the cost of energy is not competitive yet in the open marketplace. So to be successful currently, you need some kind of feed-in tariff, tax incentive, federal funding to offset that difference between the market rate of energy and the cost of energy from these marine turbines. And so what the Department of Energy is looking at are these powering the blue economy applications, where instead of just producing electricity for the terrestrial grid, they're looking at where can marine energy provide core and key power in these sort of niche markets. And so one of them that you touched on is in this isolated communities concept, where communities that are either powerless or using diesel gensets where the diesel is being brought in from very far away, can they tap into their local resources to power that community? On the power at sea side, there's a lot of work in ocean observing where marine energy can provide power at sea for wave buoys that are doing monitoring. They're looking at charging AUVs and UUVs underwater, using wave energy as an example. And a couple mechanisms that are being used include prizes in these competitions. And so the Marine Energy Collegiate Competition is one that the DOE just rolled out. The University of New Hampshire has a team that was selected to the 17 finalists for that competition. The final judging is in May. So, hopefully UNH is successful in that effort, but it's something you guys are directly involved in here on campus. And then another one that I think is a cool overlap for this Center for Coastal and Ocean Mapping, along with ocean engineering, is the Ocean Observing Prize. And this is a prize where the Department of Energy has gotten together with NOAA's Integrated Ocean Observing System, and they're looking at an integrated marine energy powered ocean observing system. So instead of having minimal battery life, you can extend the missions, you can increase the amount of assets on your buoy by using that wave resource around the buoy to power the systems on the buoy. So these are some of these other sort of off-grid applications that you can really use marine energy and can help commercialize the sector. So that's kind of where we're going. Any questions, comments on like where we see us going and the vision that we have as an industry? Because if not, we'll talk about how you actually get there. And that is the tough one. So the first, yeah, please.
Well, I think you're actually about to talk about it. But I was wondering right now then, what's like the mechanical and technological barriers that are really holding back the explosion?
Yeah, mechanical and technical barriers. So the one that I like to talk about is that usually in the ocean, people avoid the places that have the fastest tides and have the highest waves. So you are doing the exact opposite of what has been traditionally done in the maritime space. So there are some purely technical challenges to overcome in these unbelievably highly energetic environments. So it's improving our understanding of fatigue loads on blades, for example. It's understanding corrosion. It's understanding how materials behave of a long-term submergence in salt water. That's the tidal side especially. For tidal and current, as I talked about, these are all these rotary machines. And so that's very well understood. Gearbox, generator, just like a wind turbine. Most wave devices are linear motion. They're not rotary motion. And so a big technical challenge on the wave side is how do you convert that linear motion into the rotary motion that most of our generators are? And so there's a lot of work being done in hydraulic pressure related systems for wave energy, where that linear motion is converted into a hydraulic pressure, and that hydraulic pressure is used to run something else. I talked about these oscillating air columns. So instead of having the waves themselves drive something, you let the air push up and down, and the air rushes through an air turbine, which is rotary motion. So for the wave side, that's a big one, is how to convert this linear or oscillatory motion into a rotary motion that's more typical of the generators that we have in the marketplace.
Okay.
So those would be a couple that come to mind right away.
Gotcha, thanks.
Mm-hmm. So yeah, please.
So I don't know anything about energy, but do people ever use internal gravity waves for energy generation?
I've not really heard of that yet.
I don't know if it's just they're a very long wavelength.
Yeah, that's a fascinating idea. No, I don't know about that. We should talk about that afterwards. Oh, wait, so hold on. So how are we going to get there? So there's 4 key areas I want to focus on. One is the role in the US that our Department of Energy plays, and they are spending a huge amount of money in this space. And Martin's getting some of it, and I know other people around are getting it. There's a lot of money here, and I want to show some of the ways the Department of Energy is directly funding the commercialization of this industry. I am industry, so I want to talk about the role that a trade association can play, which I know is probably not usually talked about in an academic setting, but trade associations really do play an important role in commercializing industries. And I'll talk about what the US Trade Association is doing to support this. And then I'll step back out again to that international space and talk about how this Technical Committee 114 is writing standards for marine energy. Those standards play a huge role in commercialization. And lastly, we'll talk about how certification plays a role. And again, certification is the third-party verification of compliance to those standards. So it's one thing to follow a standard. It's another for an independent third party to come in and say, yes, you did comply with that standard. And we'll talk about the role especially that certification plays in reducing risk and increasing confidence in the marketplace, which is really one of the key drivers to commercializing any industry. So DOE, recently, last 5 to 10 years, they set up a specific Water Power Technologies Office, or WPTO. The Water Power Office covers both conventional hydro and the marine energy sector. Obviously, I'm most interested in the marine side. And so you can see they've got some key tenets that the DOE is working on: foundational R&D, technology-specific system design and validation, reducing barriers to testing, and then data access, analytics, and workforce. And the workforce piece is really key. And I will talk about that towards the end, about the important role that the talented workforce plays and the jobs that are available out there. So one of the ones that the DOE is funding, which is really interesting, is the Waves to Water Prize. And this is looking at innovation in the desalination space. And so they're looking at taking wave energy converters, and instead of producing electricity, they directly desalinate water. So you deploy these wave energy converters, they use that mechanical energy and run a reverse osmosis on the salt water that it's residing in, and out comes clean water with no energy input other than the waves themselves. This prize just finished at Jeanette's Pier in the Outer Banks of North Carolina. There were 4 different devices that all delivered clean water to the North Carolina coast from the waves offshore. So if you're interested in that prize and the sort of outcomes of that, I'd encourage you to take a look at that. From a testing and,
Waves to water, we had Water Bros and Wave Tech here. John was doing the testing with them.
Nice. So the Water Bros come out of North Carolina. I know those guys at UNC Charlotte, right? Yeah, that's awesome. So there's a connection right away to New Hampshire with that Waves to Water prize. One of the key things I talked about with DOE is the testing infrastructure. So PacWave, for those who don't know, is a massive wave energy test facility being built off the coast of Oregon. It's permitted for up to 30 megawatts of wave energy conversion with up to 8 berths for different wave energy developers to come in and test their wave devices in a federally supported test facility. There are other models for this globally, but this will be the first large-scale test facility we have in the US. They just finished pulling power cables to shore for that site. And we hope to have the first wave converters in the water in the next 1 to 3 years, demonstrating and proving the commercial viability of these wave energy devices. The Teamer program is another DOE funded effort, which is reducing barriers to testing. So it's a network of test facilities where developers can have their devices tested for free. So if you have a device, the DOE will pay the test lab to do the testing for you. And then the bottom one, which I think is really important for this audience, is the University Marine Energy Research Community, or UMERC. And so this is a network of all the universities in the United States that are looking to align their research priorities, looking to identify gaps in the research going on around the US, and looking to identify redundancies in research that's being done to try to prevent the same research from being done over and over and over again across the suite of universities in the US. I'm assuming, Martin, that y'all are members of UMERC already? Yeah, good. But so for folks who may not be familiar but are interested in marine energy, you can join through their portal and you'll get updates. There's job boards, there's chats, there's all kinds of interactive features so you can connect with the university research community here in the United States. Then we have the 4 research centers. And I'm obviously proud to talk about AMEC, which is the Atlantic Marine Energy Center, of which UNH is the lead entity. Is that right? Yeah. And so it's a partnership, AMEC, with Lehigh University, Stony Brook University, the Coastal Studies Institute in North Carolina, and then the University of New Hampshire. This is the newest marine renewable energy center formed in the United States. And I know it's something that Martin's really proud of. And if y'all didn't know about AMEC, Martin is certainly the person to talk to about this and learn more about AMEC. Yeah, you don't get to talk now, though. Then there are 3 other university-led research centers. In the Southeast, Florida Atlantic University runs a research center that's primarily focused on the Gulf Stream and tapping the Gulf Stream and ocean current for marine energy resources. Hawaii is doing their own Hawaiian Research Institute that focuses mainly on wave, but to some extent on that OTEC, or ocean thermal energy conversion. And then in the Northwest, you have a collaboration with Oregon State, University of Washington, and University of Alaska Fairbanks. And they're looking at a suite of marine energy technologies for the Northwest. So, just wanted you to be aware of all of this research and coordination that's going on all around the US. And, this is how you get there. One example, there's more and we'll talk about those, but having aligned research priorities, having centers of excellence, having test facilities. These are all mechanisms that get you that vision, that get you to that vision. So we'll switch now to the trade association. The Marine Energy Council is actually a part of the National Hydropower Association. So we went in under this mega umbrella of the conventional hydropower space. You can see it aligns with that DOE structure where you've got water power and marine energy under the same office. So aligning some of our lobbying and outreach efforts under a single umbrella organization has proved to be really valuable. There was this commercialization strategy developed. So again, a map. How are we going to get to these ambitious visions that we have? And this commercialization strategy outlines 10 specific federal actions that can be taken, as well as these capacity targets that I showed you. And then literally it developed key talking points so that when developers, when researchers, when the public are talking about marine energy, there is some common and consistent language and terms that are being used. And I think it's important to show these. So what are these key talking points? So one is that we have a goal of generating 1 gigawatt of electricity by 2035. And that has meaning to people. Like they want to know, what are you going to accomplish? And so putting these capacity targets does help because it gives you something to achieve, something to strive for, that point B, if you will. We definitely talk about increasing technology advancement and technology support. And so you can see a lot of what I've just talked about directly go to advancing technology and increasing access to testing. We're looking for a clear, timely, and predictable regulatory framework. I didn't have time today to really get into all the regulatory and compliance issues around marine energy. We could have like another hour seminar just on the permits that you need to put something in an ocean or in a river to produce electricity, but that needs to be streamlined. And so that's another key point to get this industry commercialized. And then the bottom one is about a fair incentive regime structure. That goes back to my discussion of tax incentives, feed-in tariffs, other economic and political mechanisms that can be adopted that help bring the cost to be competitive in the marketplace, at least in the short term. So then something that is near and dear to my heart is IEC, which stands for the International Electrotechnical Commission, and their Technical Committee 114, which writes global consensus-based standards for marine energy. I have the honor of being the chair of this technical committee. So I manage a group of nearly 200 subject matter experts from over 200 countries, nearly 30 countries that are developing a suite of standards that we'll talk about. And these individual subject matter experts are organized into these working groups where specific technical details are written down and codified. And I'll show you some of those specific technical standards that are being written. You can see we liaise with a large number of international organizations. We work closely with PV and wind, which you've just seen the examples of. We leverage knowledge of acoustics from other standards organizations. ISO is the International Standardization Organization, which is oftentimes the group that most people are familiar with. Many people have seen ISO 9000 as an example of a quality management standard. We also liaise with the International Energy Agency and some other global organizations. To date, the group has published 20 technical specifications that cover a range of technologies, and we'll talk about those in a second. We have also agreed globally on a set of terminology for the industry. Very important that everyone uses the same language when you're talking about this across the world. So if you're interested in some of the terminology that's been agreed upon globally, you can just Google IEV Part 417. It'll take you directly to a link with a suite of terms that the globe has agreed are the standardized terminology for use in the industry. Really helps in that commercialization path. As they say, a picture says 1,000 words. So here is the geographic distribution of what are called the participating member countries. So these are the countries in the world that participate actively in the development of these standards. You can see we have the largest European marketplaces. We have the largest Asian and Australian marketplaces, and then Canada and the US. You can see we have a huge gap in South America, huge gap in the most of Africa. So that's something as chair that I really work on, is trying to increase the diversity of knowledge, bring more countries involved. And there are a lot of countries not shown that have marine energy aspirations and or projects ongoing. I mentioned there were 29 countries, so 12 of them are what we call observer countries. And literally that pretty much gets you all the rest of Europe. So you've got like all of Europe, most of North America, and then you do get Brazil as a no member. A big gap, like I said, is South America, and in particular Chile is a country where there's quite a lot of activity in marine energy. So I've got my work to do to keep building this group of people, but it's a really cool group. So we develop standards. Some of them are resource agnostic. So these are independent of the resource that you're tapping into. So things like design, things like the measurement of loads, Things like the power quality, right? So these are things that affect all different resources. And so we consider these to be our resource agnostic standards. And then we also have a suite of resource specific standards. So we have a design standard for an OTEC plant, if you were an OTEC developer. We have a suite of standards that are specifically designed for wave energy converters. We have a suite of standards that are specifically designed for tidal energy converters. Very proud to say Martin led the writing of the -202 standard, which is right here for tidal energy converter scale testing. So a lot of the work that came out of this laboratory fed the global standard for how to do scale testing of tidal energy converters. So UNH very much globally relevant on a number of different levels, as I think you've seen in these slides. And then river energy is in our purview. This is river energy without dams or impoundments. So these are the devices that capture the kinetic energy that's existing in a naturally flowing river and converts that into electricity or some other usable form of energy. So the last piece of my talk is on certification, which I mentioned relates to the third-party verification of compliance to these standards. Marine energy, solar energy, and wind energy have come together to form a global system for certifying renewable energy equipment. This is a stamp that is physically put on a device that says you comply with standards. If anybody looks at their cell phone, their laptop, their battery pack, their smartwatch, you will see a number of stamps on them. All those stamps are this. They are a third party that verified compliance to standards, which means the performance, the safety are at a minimum level that is acceptable for human interaction. Really, really important as we commercialize the sector. And so similarly, picture says 1,000 words. We're a smaller group, so only 6 countries are participating. But I think what's more important is that in those 6 countries, we have the world's leading certification bodies and test laboratories involved. So in the US, we have PacWave, which I talked about, and we have NREL, which is the National Renewable Energy Laboratory. For those familiar in the UK, we have EMAC, which is the European Marine Energy Center, which is the premier test facility for all marine energy devices globally. If you look on the certification body side, maybe you've heard of them, maybe not, but DNVGL, one of the largest certification bodies in the world. Lloyd's Register in the UK, Bureau Veritas in France, the American Bureau of Shipping in the United States. These certification bodies are the drivers of risk reduction. If you can get a third-party certification body to verify your product, it will have an easier time entering the global marketplace, it will get better terms on its insurance and investment, and it is more likely to reach a commercial stage than in the absence of those third-party verifications. So this work is incredibly important as we try to commercialize the marine energy sector. Just quickly, this is kind of what goes into getting what's called a type certificate. A type certificate is sort of the fundamental concept where one turbine can get tested and then you can roll them off your factory line, if you will. And what you can do is for each of these steps, you can map specific standards that are developed by TC 114 that allow you to verify the design basis, verify the assessment of the design, verify the power performance or the acoustic emissions or the power quality. And this suite of standards together will lead to the issuance of a certificate that is kind of the ultimate trust that the industry needs to really build up. I'll skip this. But with that, I'll conclude. We've got 5 minutes so we can do some Q&A and sit and chill for a little bit. But so I hope you took from this, right? First of all, there's a huge market and a global market for marine energy, and it's vastly all over the world untapped. So there's a huge opportunity and a tremendous resource available in the marine energy space. We talked about this. There's a lack of technology convergence across the space, which generally leads to this perception of high risk. And so a lot of what we're doing to de-risk is working towards commercializing this sector. We have identified capacity targets, and there is significant funding available in the space to advance the technology. Standards and certification that I just touched on play a really critical role in reducing risk and increasing confidence. Again, it's all about reducing risk and increasing confidence in the marketplace. And lastly, that workforce development is such a critical piece. And I literally get an email, I would say once a week or once every 2 weeks, asking if I have any talented candidates looking for jobs. So if you are interested in getting into the industry, it's a great time for it. There are tons of startups. You have to be a bit of an entrepreneur and you have to be a bit of a risk taker yourself, because you're certainly not going to your Lockheed Martin or to some huge, really well-established Google type company, right? Like Verdant Power is 11 people. A lot of those companies I showed are relatively small, but there are opportunities to work there and to really meaningfully impact that company on a day-to-day basis. And I know in my experience, I was doing everything. Like some days I was on a boat taking ADCP data. Some days I was writing MATLAB code. Some days I was in the yard operating a forklift. You know, some days I was meeting with the Federal Energy Regulatory Commission. Other days we were counting fish. And so, you know, that environment, like hands-on, really impactful, is available in this space. And a piece of advice I give to folks a lot is that it's very difficult as a first out of undergrad to enter into this market because the companies are looking for people that are like work ready and can show that autonomous, independent, self-motivated. Coming out with a master's or a PhD, that equates to multiple years of work experience. And so when you come out with a master's or a PhD in this field, you are an absolute hot commodity in the marine energy space. And whether you want to work on the West Coast, the Northwest, the East Coast, abroad, there are tons of opportunities in marine energy to work in the industry if that's something you're interested in, if you don't decide to stay in academia. I know a lot of PhD candidates, you know, are going to continue in academia. And if that's the case, you know, I think there's a lot of chances for these universities to engage with the developers. Like we need that expertise to come into the industry and not just stay in the lab, not just stay in the classroom. And so even if you do stay in academia, like I think it's really important that you publish those journal papers, you partner with industry on projects so that that knowledge can come out of the lab and out of the university and actually into the industry. So yeah, with 2 minutes to spare, I really want to say thank you, Martin, thank you. There's an email for me. This is a vortex being shed off of a tidal energy converter in the north of Scotland. I'm an experimental fluids person and a fluid dynamics person by trade. So I just love this photo because who doesn't love a perfectly shed vortex? So it's Friday at 4. I'm sure you guys have like dates at the bar and stuff like that. Parties to go to.
In your talk about, or your discussion about the lack of convergence in the technology, and you said that, if I got this right, that the stream stuff is more or less converged, but the other modes of generation really have not. You have a gut feel of how that's going to evolve?
So you nailed it. The current space, I'm relatively confident that it's going to be the vast majority are going to be horizontal axis, 2 or 3 bladed rotors, gearboxes to generators. You know, I know that ORPC is looking at a helical Darius type. You know, Nicole is doing some research on H-type Darius, and those will have a role. So I don't think it's only going to be one, but I think it's going to be those 2 archetypes. It's either going to be a Darius style or it's going to be like a horizontal axis, 3-bladed, 2-bladed. Wave is really different. And I'm not sure wave will ever converge, to be totally honest with you. You have deep wave dynamics versus shallow wave dynamics. You have, you know, some people that are much more interested in that breakwater kind of wave converter. Some people that are much more interested in that deep water converter. I think at the wave scales, you might see some convergence. So in the near shore environment where people are, you know, utilizing near shore waves, breaking waves, you might see 1 or 2 archetypes sort of take the lead. In that deep water environment, I think you might see some other archetypes start to take the lead. I think we've seen in the deeper water that the point absorber is starting to have more and more of a focus. Near shore, I think you're going to see more of this oscillating air and oscillating water column. Leveraging like breakwaters and jetties where you can put in infrastructure on land, but still take advantage of the marine environment, for me is a very natural one, especially as you're looking at sea level rises and these increasing storm events. As coastal communities look to build protective barriers and look to try to mitigate some of the risk of those mega wave events, integrating wave converters into those jetties and breakwalls and seawalls, I think for me is a really natural fit. I think another interesting space that we haven't talked about, there's 2 of them, are floating solar. And so they're looking at putting solar panels on lagoons, out in harbors, out in oceans. And that would give you an opportunity to co-locate potentially some wave energy converters with your floating solar. And then also leverage the mechanical moorings that are much more marine energy. Like a solar PV guy literally knows nothing about an underwater mooring, whereas a marine person knows nothing about a, you know, thermocrystal PV panel. So that's like a really neat place where marine and solar can kind of come together. Another one which people are really looking at are these hybrid wave wind systems, where the floating platform for the wind turbine also is embedded with wave converters. You can take advantage of the power infrastructure because you've already got a mega power cable running to shore. Another one would be to like ring your wind turbines with wave converters. And then the wave converters damp some of that wave energy with the extraction. And that lowers some of the wave loading on the tower, which gets you some better fatigue life, for example, on an existing wave tower or wind tower or wind platform. So I think WAVE is at a lower TRL, which is technology readiness level. So I think WAVE has further to go in terms of A, converging, and B, finding these markets where they can leverage some other assets to prove the reliability and the viability of the technology. I think current in the title is at a higher TRL. We're seeing much larger projects. Like there are 2 or 3 400 plus megawatt projects in the pipeline for title alone. The 30 megawatts of pack wave is like the largest wave project in the world, or would be if it was fully installed. So there's kind of a couple orders of magnitude difference. You know, there's probably 2 to 3 gigawatts of tidal energy power in the process or already being consented. Whereas wave, you're talking about very small arrays and very small projects right now. Yeah. Oh, yeah, go ahead, please.
Question, kind of the grid scale, grid size devices that have been tested. What has kept them, I guess, in the water? Like, are they breaking down? Is that what's keeping them from getting like 5 to 10 year life cycles of them, or is it just like,
Yeah, there's a couple things that keep these devices from being in the water for a really long time. One is that most of the permits to date are not long-term permits. The regulatory community does not have the confidence that these devices are benign and are compatible, so they're not willing to give you a 40-year license right now. So you learned about the right project in Vernon, that was a 10-year pilot license. So after 10 years, full stop, you had to take the machines out. So that's one piece, is that oftentimes the permits are limited on purpose. There are also phased build out requirements. So you can't just put in 100 turbines right off the bat. You can put in 1, and then you can put in 5, and then you can put in 10. So that's another piece that kind of keeps, because you're always like moving to the next phase. Financing is another huge one. It's expensive to operate these plants for long term. And if you're not generating enough revenue from the power you're producing, then it's a sunk investment. And especially in this current economic landscape where low risk, high return, like I saw a thing, I'm going to get the numbers wrong, but I'm just going to do some more. I think I saw that there's $3 billion invested in energy infrastructure globally. And there was $30 billion invested in cryptocurrencies and NFTs, just those two. So there's a 10x interval of investment in NFTs and crypto over traditional energy infrastructure. And so, I mean, you're fighting for a diminishingly small pot. And because of 2008, the dot bomb and, the housing bubble, you have risk averse investors, and they're looking at this like flash in the pan, let's make hella money right now on this like bubble. And they're not willing to put in like a 40-year investment in a long-term marine energy project. Positive flip of that is that major national pension funds are starting to invest in wind farms. And that was a huge milestone for the wind sector. It's when the Norwegian state pension fund, like literally invested, a huge amount of money in a 40-year wind farm. And that kind of state pension fund is one of the only probably investor models that could possibly take that kind of risk, like JP Morgan Chase just isn't ready to do that. And so when you look at the industry, there's really no venture capital money and there's really no institutional money. There's no big banks. So what you're mostly looking at are angel investors, family houses or philanthropic investors, and then this new like ESG, which is on environmental, sustainable, and governance funds. So it's changing the paradigm of investors out of make hella money tomorrow into like, what are the goals that I have as a long-term investment strategy? And how does that mix with climate initiatives? How does that mix with circular economy initiatives? How does that mix with health and well-being initiatives? So there's a lot of like confluence of things that kind of prevent that. And then failures. I mean, that's kind of the most obvious one. I probably should have started there. Like things have been breaking. I mean, I'll add one more and then I'll come to you. The other one is that a lot of times the first design that goes in is not even close to the final design. So you do a year and you're like, oh, we learned a ton. Let's take it out. Let's swap a gearbox. Let's try a different blade and let's run that for a year. And I just heard from somebody that they have been developing technology for like 10 years or 15 years, and they're just getting to a product that they think is a stable product. So you really wouldn't want to run your beta version for 10 years. You want to do your beta version for like 2 to 3 years, get it out, and then get your commercial product in for the 10 to 15 to 20 years.
When you talked about that panel you were on, the IEC, the one that you're in charge of, you mentioned the different countries involved in the observing countries.
Mm-hmm.
When you say observing, are they just seeing what the other countries are doing
Yeah.
and hoping to put in a plan for themselves? Like, I guess what?
Yeah. So the IEC is a membership-based organization where the countries are the members. And to be a participating member, it carries specific responsibilities, including voting on all documents, attending an annual meeting, and nominating subject matter experts for all of the activities that are happening. So when you step up to be a peer participating member, it has mandatory participation requirements. And a lot of times either smaller countries or developing countries or countries that don't quite have the infrastructure or the industry aren't ready to put up the financial resources to physically travel to all these different countries for meetings. They may not have the infrastructure to vote and to manage all of these experts. In the US, for example, we get funding from the Department of Energy to support our experts. So we have resources. NREL in Colorado serves as our administrator. So they manage all of the voting, they manage all the experts, they nominate people. Whereas the observers, they don't have to vote. They don't have to attend meetings. They can if they want to. They don't have to comment on documents, but they can if they want to. So it's kind of like an entry-level engagement where it's not quite so onerous and resource intense on the country. The goal is to get all of these to become P members, for sure. And we've had some good effort with that, like Belgium and Italy, as two examples, both started as O members. And as their industry gained footing and as they felt more confidence, really, they upgraded their membership from O to P. And I didn't talk about it, but in the blues, the light blues are the affiliate programs and the dark blues are the full members. So like 97% of all the world's population is covered by countries in the IEC. And it's something like 99% of all electricity generation in the world is covered by IEC standards. But so the dark blue are the ones that have full membership in the IEC at large. And the light blue are ones where they're even just trying to figure out how to engage at the IEC at all. And then on each technical committee, you have kind of that same process mirrored, where some countries are just trying to figure out how to get involved. And other countries are like, we're here, here's an expert, and here's what the standard should say. How many countries did you have on yours? In your PT? 5, 6?
Probably 8.
So of those 17, Martin got 8 of them that decided they had the enough expertise in scale testing of tidal energy converters, which obviously like, that's a pretty little, that's like pretty far down the granularity chain to be like, we have an expert on scale testing of tidal energy converters. And I saw a question. Yeah, please.
Yeah, I just kind of have a question about that process. Like, is there a mechanism that allows folks who are like not necessarily invested in that industry to comment on the technical guides that are produced and to provide input? And the only reason I ask is I know a totally different sphere, totally different industry for which there's a bunch of people who complain routinely about the standard that was produced because it was designed by a bunch of people who knew a lot about the specific thing that they were doing, but missed a whole swath of modern technology that had overwhelmed that initial thing. And so they missed all of that input. I'm just curious if there's a mechanism for that.
So there are 2 mechanisms. One is the historical mechanism, and that is in each country you have what's called, or in the US, we call it a technical advisory group. And so in the US, our TAG is the acronym, is 150 people. And of those 150 people, only about 25 of them actually participate at the international level writing standards. So those people bring back the work at the international level and disseminate it to the entire technical advisory group so that 150 pool of people can opine and chime in. Now, obviously that one is limited because you have to be on the technical advisory group. But what the IEC has actually just done is started a public commenting phase for standards. So now through the IEC, any member of the public can create a login account and can comment on the standards that are being written. Those comments are funneled to the national committee of where that person lives. And the national committee has some authority to kind of make sure that this wasn't like some totally random person that was like, I don't like the color blue, you need to paint that red, right? Because like, that's not exactly what we're looking for, but it does capture exactly what you're talking about, which is somebody who didn't know there was this technical advisory group, but all of a sudden found this standard and is like, dude, this doesn't work. They can go to the IEC and they can put in that feedback and it'll get funneled back to the national committee and then on to the group itself. I would tell you, I've been doing this for like 15 years. So if there's a specific standard that you have an issue with, I would love to hear it. And I could literally probably connect you to the people that wrote it. And I would be more than happy to make that connection.
Okay. Yeah, there's not in this.
No, but it could be in anything. I mean, the IEC touches anything with electrotechnical. So, yeah.
Question in the chat.
Oh, yeah, go ahead, chat.
So Louis said, I thought I saw on the slide that Micronesia and Samoa produce large amounts of tidal energy compared to other U.S. territories. Are there regulatory factors key in this outcome in these territories? If so, what are these factors?
So close. Micronesia is down in the lower left. It's the 1133 box. That gray color is ocean thermal energy conversion. So 100% of the resource in Micronesia, according to this estimate, is in ocean thermal and not in tidal. I still can answer the second part though, because it was something about regulatory.
So the regulatory factors key in this outcome, so that they're making more because there's regulatory factors, I think is what he means. If so, what?
So, okay, so here's one question. So this is not produced. And who's this? I'm sorry.
His name is Lewis.
Lewis. So Lewis, this is not produced. This is available resource. So we would have to go look at what they were actually producing of this available resource. And I have to be honest about Micronesia, I don't know the regulatory framework as well as I know it in the United States. Ironically enough, my father-in-law, I believe, is on, and he's an expert in Micronesia as an anthropologist. So Glenn, if you're still listening and you want to chime in on this chat to Lewis about the regulatory framework in Micronesia, I would love that. I'm literally not lying. I literally could not make that up if I wanted to.
I was wondering more about this ocean thermal energy. Like, what is the equipment that they're using for the conversion? How are they actually going through this?
Yeah, so OTEC basically requires putting a massive pipe down, and they pump the cold water up and they lower the warm water to the bottom. And then it's one of the fundamental thermodynamic cycles that allows you to extract energy. It's like a steam turbine.
Right.
We have a hot side and a cold side. I think it's a Rankine cycle, but I'm really nervous because I haven't taken thermodynamics in a really long time. It is a Rankine cycle.
Runs on ammonia.
Yeah, ammonia, there you go. I don't know that much about OTEC. I think OTEC, did Glenn chime in? That would be so cool if Glenn chimed in. Nope.
Lewis said thank you.
Yeah, you're welcome, Liz. Well, that's what's up. I hope that was useful for y'all.